Hello, how are we doing? So we're up to module 4 of ENSA, talking about ACL concepts. So we're going to explain how ACLs are used as part of network security policy. We'll talk about the purpose, the wildcard masks used in ACLs, guidelines for ACL creation, and then types of IPv4 ACLs. Okay, purpose of ACLs. So an ACL, or access control list, is a series of iOS commands that are used to filter packets based on information found in the packet header. By default, a router does not have any ACLs configured. When an ACL is applied to an interface, the router performs the additional task of evaluating all network packets as they pass through the interface to determine if the packet can be forwarded. An ACL uses a sequential list of permit and deny statements known as access control entries. Note, access control entries are commonly called access control lists because of the command. When network traffic passes through an interface configured with an ACL, the router compares the information within the packet against each access control entry in sequential order to determine if the packet matches one of those ACEs. This process is called packet filtering. So, several tasks performed by routers require the use of ACLs to identify traffic. And so this is another purpose for it. And so you can limit network traffic to increase network performance. You can provide traffic flow control. You can provide a basic level of security for network access. You can filter traffic based on traffic type. You can screen hosts to permit or deny access to network services. And you can provide a priority to certain classes of network traffic. So these are all what ACLs can be used for. And so not only just packet filtering on interfaces, there are other purposes as well. So knowing how to create an ACL is quite important. All right, so packet filtering, of course, is what we're mostly talking about today. And so packet filtering controls access to a network by analyzing the incoming and or outgoing packets and forwarding them or discarding them based on the given criteria. Cisco routers support two types of ACLs, so standard ACLs, which filter at layer 3 using the source IPv4 address only, while extended ACLs can filter at layer 3 using the source and or destination IPv4 addresses, but they can also filter at layer 4 using TCP and UDP ports and optional protocol type information for finer control. So yeah, the extended ACLs are a much more precise control. So ACL operation. So they define the set of rules that give added control for packets that enter inbound interfaces, packets that relay through the router, and packets that exit outbound interfaces. ACLs can be configured to apply to inbound traffic and outbound traffic. Note, ACLs do not act on packets that originate from the router itself. An inbound ACL filters packets before they are routed to the outbound interface. An inbound ACL is efficient because it saves the overhead of routing lookups if the packet is discarded. An outbound ACL filters packets after being routed, regardless of the inbound interface. So, when an ACL is applied to an interface, it follows a specific operating procedure. Here are the operational steps used when traffic has entered a router interface with an inbound standard IPv4 ACL configured. So, the router extracts the source IPv4 address from the packet header. It starts at the top of the ACL and compares the source IP address to each access control entry in sequential order. When a match is made, the router carries out the instruction, either permitting or denying the packet, and the remaining access control entries are not analyzed, so it's first match. If the source IPv4 address does not match any access control entries, the packet is discarded because there is an implicit deny all access control entry automatically applied to all ACLs. The last access control entry of an ACL is always an implicit deny that blocks all traffic. It is hidden and is not displayed in the configuration. Note, an ACL must have at least one permit statement, otherwise all traffic will be denied due to that implicit deny access control entry. So that's a hard and fast rule. Always have to have at least one permit statement. All right, so wildcard masks. So a wildcard mask is similar to a subnet mask in that it uses the ANDing process to identify which bits in an IPv4 address to match. Unlike a subnet mask, in which a binary 1 is equal to a match and a binary 0 is equal to a not match, the wildcard mask, the reverse is true. And so an IPv4 access control entry uses a 32-bit wildcard mask to determine which bits of the address to examine for a match. Wildcard masks use the following rules to match binary 1s and 0s. And so the wildcard mask bit 0 will match the corresponding bit value in the address, while with the wildcard mask bit value of 1, it will ignore the corresponding bit value in the address. So if we have a wildcard mask of quad 4, it will be 32 zeros. And so, of course, a 0 means match. And so all 32 bits must match. And so basically, you are specifying a host. And so you might be permitting or denying a particular host from doing something. And so that is the wildcard mask you would use. There is another option, but we'll talk about it later. Okay, so the next one is 000.63. And so we've converted the last octet into binary. And so as you can see, it's 2 zeros followed by 6 ones. And so basically here, the first 3 octets must match, of course, because they're all zeros. And in the 4th octet, the first 2 bits must match. The last 6 bits do not need to match. And so this would be a range of addresses. And so basically there would be 64 addresses that would match this. And so that could be a subnet, let's say. All right, so the next one is 00015. So again, the first 3 octets are a complete match, have to be a complete match. With the last octet, the first 4 bits must match. The last 4 bits do not need to match. We don't care about them, basically. So, and so again, that would be a range of 16 addresses that would match. And so again, a smaller subnet, I suppose. Now, 248. And so, as you can see here, that's one you probably wouldn't use all that often, but anyway. And so the first 6 bits must match. Oh, sorry, the first 3 octets, of course, must match. And then the first 6 bits don't need to match, but the last 2 do. Now, you might have an addressing scheme where you leave the last 2 bits as zeros, and that might be, I don't know, your routers or whatever it might be. Might be set like that, but it's a pretty strange one, that one, actually. I've actually seen access control lists written where you have maybe an odd subnet or an even subnet. That's been done before. And so maybe your odd subnets are student subnets, while the even ones are staff subnets or something like that. So, anyway. Okay, so in this last octet is probably one you will use more often. Sorry, last example is 000.255. And so this would match a /24 subnet, basically. So the first 3 octets would match. The last octet does not matter. So that would be an entire /24 network that would match. So that's one you probably will use regularly. Okay. How do we get a wildcard to match a host? And so I think the first example was actually that. And so as you can see, we've got the sample address of 192.168.1.1. Oh, sorry. Let's go to it. So assume ACL 10 needs an access control list that only permits the host with the IPv4 address 192.168.1.1. And so, of course, 0 is a match and 1 is an ignore. To match a specific host address, you would have all zeros. So quad 0 or 32 zeros in actual fact. When the access control entry is processed, the wildcard mask will permit only that host. The resulting access control entry would be access list, that's the command, 10, so that's why it's access list 10. The action is permit, and then the supplied IP address is 192.168.1.1, and the wildcard mask, shouldn't have it on the end, but anyway, would be 4 zeros, and so that, of course, that translates to 32 zeros. And so, of course, when you look at this, all 32 bits must match the sample to actually get your permitted address of that. Now, wildcard mask to match an IPv4 subnet. So it's what I was talking about a bit earlier. So access list 10 needs an access control entry that permits all hosts on 192.168.1.0/24 network. The wildcard mask of 000255 stipulates that the very first 3 octets must match exactly, but the 4th octet does not need to match at all. And so when processed, the wildcard mask of 000255 permits all hosts in the 192.168.1.0/24 network. The resulting access control entry in ACL 10 would be access list 10 permit 192.168.1.0 and 000.255. And so yeah, it's just the first 3 octets that must match. Last one, again, we don't care. It can be any number. All right, so wildcard mask to match an IPv4 address range. And so maybe you've got a range of /24 subnets that you wish to match, and that's entirely possible in one line. And so ACL 10 needs an access control entry that permits all hosts 192.168.16.0/24 all the way through to 192.168.31.0 subnet. So when processed, the wildcard mask of 0015.255 permits all hosts in the range 16 through to 31 in the 3rd octet. The resulting access control entry would be access list 10 permit 192.168.16 and then 0015.255. And so, of course, here is your 16.0. So 192.168.16, of course, is there. So that's the last bit that we need to match. And so, of course, with these possible changes, we can go anywhere from 16, which is of course what we see here, is all the way to 4 ones in this last 4 bits, and that would be 31 as it says. And so of course the 4th octet can be absolutely anything, it will always match. Okay, so calculating wildcard masks can be challenging. One shortcut is to subtract the subnet mask from 255.255.255.255. And so assume you want an ACL to permit access to all users in the subnet 192.168.3.0. Calculate wildcard mask by subtracting 255.255.255 from 0 from 255.255.255.255. This produces a wildcard mask of 000.255. Now, of course, that's a wonderful mathematical process to do that, but of course, basically, my personal thing is you just invert it. And so any bit that's 1s in the subnet mask would be 0s in the wildcard mask, and anything that's 0 in the subnet mask would be 1 in the wildcard mask. And so anyway, so assume you wanted ACL 10 to permit network access for the 14 users in the subnet 192.168.3.32. And so, of course, the mask is 255.255.255.240. And so the end result mask would be 000.15. And so on. So another example, you needed to permit the ACL 10 only networks 192.168.10.0 and 11.0. And so basically you could do 192.168.10.0/23. So of course, when you look at the binary, 10 of course is 1010, and 11 of course is just add 1 to that. And so of course that last 0 would become a 1. And so it's only that 24th bit that changes between the two. And so if you match the first 23, that will match. And so of course you've got the last bit in the 3rd octet and all of the 4th octet do not need to match. Okay, so Cisco iOS provides 2 keywords to identify the most common uses of a wildcard mask. And so you can actually use the term host, which this keyword substitutes for the quad 0 mask. And so, of course, when we were looking at the examples earlier, when you had quad 0, you were talking about one host. And so instead of having the mask of quad 0, you can just say host 192.168.1.1. And it also makes it more self-explanatory. It's English. And so it's saying this host will be permitted or denied. And so it just makes it a lot easier to understand. And then, of course, the wildcard mask of all ones will actually match every address that there is. And so any host would be permitted with that. And so why not just say any? And so that's actually the implied deny statement at the end is deny any. Okay, now guidelines for ACL creation. Now there is a limit to how many ACLs you can apply. So there is a limit that, for example, on a dual stacked IPv4 and IPv6 router, you could have 4 ACLs applied to one interface. But basically the rule is one access list per direction per interface, or per interface per direction, either way. And so of course each interface has inbound and outbound. And so for IPv4, you can have 2, one inbound and one outbound. And then, of course, IPv6 is a different protocol. And so one inbound and one outbound IPv6 ACL as well. So ACLs do not need to be configured in both directions. The number of ACLs and their direction applied to the interface will depend on the security policy of the organization. Okay, so best practices. Using ACLs requires attention to detail and great care. Mistakes can be costly in terms of downtime, troubleshooting efforts, and poor network service. Basic planning is required before configuring ACL. Okay, so you should be basing your ACLs on the organizational security policy. And so basically there's a plan. In that security policy, you should be defining what traffic is allowed, what traffic is not allowed. And so that should actually be your basis. And so you should have planned it first, as it says. Write out what you want the ACL to do. And so basically, block this traffic, permit this traffic, and so on and so forth. And so this will help you avoid inadvertently creating potential access problems. And so you could use a text editor to create, edit, and save all your ACLs. And so that gives you a library of reusable ACLs. Document the ACLs using the remark command. So there's access list 10 permit, there's access list 10 deny, there's also access list 10 remark. And so the remark of course, is not processed, but it's in amongst the ACL, and it will let you put in comments. So the following line blocks FTP traffic from getting to such and such. And so that's the kind of things you need. All right. And so test the ACLs on a development network before implementing them on a production network. And so basically, can't always do that, but you should if you can, because you don't want to kill your production network by making a mistake. We all make mistakes. All right. So there's 2 major types of ACLs, standard and extended. That's for IPv4. Now, standard ACLs, as was said before, only based on the source IPv4 address. With extended, you can have source and/or destination IPv4 addresses. You can specify protocol type, and you can also use port numbers for TCP and UDP. So extended is a lot more granular or precise, I think I said earlier. Okay, so how do we put the command in? And so, well, actually, that's part of what we're talking about here, but also the examples so far have been numbered ACLs, and so the numbers are not random. The numbers are actually serve a purpose. They actually define what kind of ACL we're talking about. Now, we've only been looking at standard ACL commands so far, and so the range 1 through to 99 is actually the number range for standard access lists. There is also another range, 1300 through to 1999. If you put 99 ACLs there, you can actually expand to that. Now, 100 through to 199 are the extended ACLs. And there is an extra list as well. and so 2000 through to 2699 is also extended. Now, if you don't want to remember those other numbers, well, I suppose you could do this command, access list ? And it will explain what they mean. But you can actually do named access lists as well. And so as long as you can come up with enough unique names for ACLs, you're all good. But we will talk about, so this slide. So name the ACLs a preferred method to use when configuring ACLs. Specifically, standard and extended ACLs can be named to provide information about the purpose of the ACL. For example, you may use an extended ACL FTP filter. So that actually describes what the point of it is. And so it's far better than ACL 100. That just is a number, not very explanatory. The IP access list global configuration command is used to create a named ACL as shown in the example. So you do IP access list extended, so you need to specify the type. It could be standard or extended. And then you give it a name. And as you can see, your config mode changes. And so you're actually changed into extended named ACL config mode. And so all commands you put in will belong to this ACL. And so you don't need to do access list 10 or access list FTP filter on every command. You can just do permit TCP. Blah, blah, blah. So this is extended, and so you need to specify protocol. Again, it starts with source address, destination address of any, and then EQ FTP. So we're permitting that. And yeah, of course, FTP uses 2 ports. And so if these are the only 2 lines in it, FTP will get through. Then there is a deny IP any that will actually follow, and that is that implied deny that we were talking about. And so Now, where to place ACLs? Every ACL should be placed where it has the greatest impact on efficiency. Extended ACLs should be located as close as possible to the source of the traffic to be filtered. Standard ACLs should be located as close as possible to the destination of the traffic that's filtered. Now, the reason for that is with extended ones, because you have far greater control and it's a lot more granular, you can control what traffic is routed, and so you can actually stop it from maybe going over these quite possibly limited WAN links. And so you're saving bandwidth on the WAN links. And so if you're trying to get this PC to that server or control what it does, you can actually do it here and they won't be routed. Now, the problem with standard ACLs is if you're trying to block traffic from this PC to that server, because you can only specify the source address, that PC won't be able to talk to anyone. And so, so you'd actually do it here on this router, probably outbound, so that you can just stop them from getting to the server, but they can go to everywhere else that they might need to go to. So it's just a matter of, that's logic, I suppose. Now, the factors influencing ACL placement. So the extent of organizational control. Placement of the ACL can depend on whether or not the organization has control of both the source and destination networks. So yes, that is an issue. Bandwidth the networks involved. It may be desirable to filter unwanted traffic at the source to prevent transmission of bandwidth consuming traffic. Ease of configuration. It may be easy to implement an ACL at the destination, but traffic will use bandwidth unnecessarily. An extended ACL could be used on each router where the traffic is originated. This would save bandwidth by filtering the traffic at the source, but it would require creating extended ACLs on multiple routers. So, so there's always swings and roundabouts involved. Okay, so standard ACL placement, as we said. Okay, so I picked the wrong one. So we're trying to control traffic from PC1's network to PC3's network. And so because it's a standard ACL, you would need to put it outbound on this gigabit interface. Because if I put it inbound here, well, they'd be able to get nowhere. Might as well just unplug it. If you put it here, well, they'd be able to talk to there, but nothing over here. if you put it here, again, much the same result. And so if you put it here, they can still talk to the server, which is apparently permitted, but they can't talk to that subnet itself. And so that's why you need to do an ACL, a standard ACL, as close as possible to the destination. So there are two possible interfaces in R3 to apply the ACL. And so it could be S011, but that would actually block the traffic to both 30 and 31. And that's not necessarily what was required, because it's supposed to just be blocking it to 30. And so outbound on the gigabit is the preferred plan, because that just blocks them from the network they're not supposed to go to. So extended ACL placement. In this case, we're going to block FTP and telnet traffic from subnet 11 to 30. And so because it's extended, you can actually specify that traffic to block and then permit the rest. You can actually put it inbound in G001, so you can save the router even having to process the routing table, in this case, for the packets, because they'll get dropped before that actually happens. And so that's an efficient way to go. Now, it's not all upside for extended ACLs. While they are a lot more granular and it gives you a lot more control, it is more processing for the router. Now, because it's actually got to dig further into the packet and compare more information, and so it is more work. And so it's not entirely good news, but I think it's probably the better solution in this case, that's for sure. So an extended ACL on R3 would accomplish the task, but the administrator does not control R3. In addition, this solution allows unwanted traffic to cross the entire network only to be blocked at the destination. So yeah, you could have done it on R3, but yeah, crazy talk. So R1 and yeah, G001 is the best solution because it's as close as possible to the source for an extended one. Okay, so that is the end. So next chapter, of course, is we actually look at implementing ACLs. So yeah, it's conceptual in this chapter. So what did we look at? So an ACL is a series of iOS commands that are used to filter packets based on information found in the packet header. A router does not have any ACLs configured by default. When an ACL is applied to an interface, the router performs the additional task of evaluating all network packets as they pass through the interface to determine if the packet can be forwarded or dropped. An ACL uses a sequential list of permit or deny statements known as access control entries. Cisco routers support two types of ACLs, so standard ACLs and extended ACLs. An inbound ACL filters packets before they are routed to the outbound interface. If the packet is permitted by the ACL, it is then processed for routing. An outbound ACL filters packets after being routed, regardless of the inbound interface. An IPv4 access control entry uses a 32-bit wildcard to determine which bits of the address to examine for a match. Wildcard mask is similar to a subnet mask in that it's used in the ANDing process to identify which bits in the address to match. However, they differ in the way they match binary ones and zeros. Wildcard mask bit 0 matches the corresponding bit, while the wildcard mask bit of value of 1 ignores the corresponding bit value on the address. Okay, so a shortcut to calculating wildcard mask is subtract the subnet mask from 32 ones. Working with decimal representations of binary wildcard masks can be simplified by using Cisco iOS keywords host and any. There is a limit to the number of ACLs that can be applied to a router interface. As I said, it's one access control list per interface, per direction, per protocol. So there is the ACLs do not have to be configured in both directions. The number of ACLs in their direction applied to the interface will depend on the security policy of the organization. Standard ACLs permit or deny packets based only on the source IPv4 address. Extended ACLs permit or deny packets based on the source IPv4 address and destination IPv4 address. Protocol type, source and destination, TCP or UDP ports, and more. ACLs numbered 1 through to 99 and 1300 through to 1999 are standard ACLs. Numbered 100 to 199 and 2000 to 2699 are extended ACLs. Named ACLs are preferred because it can be descriptive. Specifically, standard and extended ACLs can be named to provide information about the purpose of the ACL. Every ACL should be placed where it has the greatest impact on efficiency. Extended ACL should be located as close as possible to the source of the traffic to be filtered. This way, undesirable traffic is denied close to the source without crossing the network infrastructure. Standard ACL should be located as close to the destination as possible. If an standard ACL was placed at the source of the traffic, the permit or deny will occur based on the given source address, no matter where the traffic is destined. Placement of the ACL may depend on the extent of organisational control, bandwidth of networks, and ease of configuration. That is the chapter. All right, so as I said, the next chapter will be configuring ACLs, and so that's where we'll be going with that. All right, that's it for this one. Have a nice day, and I'll see you for the next chapter.